For today, we need to go back to section 7.3 for a second, and I need to rationalize some denominators I forgot about. So on number 19 and 25, I'm on section 7.3, so if you would just go back to that. I'm going to erase, because this one, 19, is not rationalized, and it does say in simplest form. Okay, so what I'm going to do here to rationalize this denominator is make it so that the fractional exponents add to 1. So I'm going to multiply by x to the 3/5 and y to the 4/5, both top and bottom. And when I do that, my result is, in the numerator, x to the 3/5, y to the 4/5, divided by x to the 2 plus 3 over 5, which is x to the 5/5, y to the 1 plus 4 over 5, which is y to the 5/5. And then that gives me x to the 3/5, y to the 4/5, divided by x to the 1st. 5 over 5, x to the 1st, y to the 1st. And that is how I would rationalize the denominator with a fractional exponent. Number 25, we also need to rationalize the denominator. And on that one, I'm going to just erase that last, answer there, because that is wrong. I mean, it's not wrong, but it's not complete. And I'm going to change this. I'm going to multiply by, now what I'm going to notice here is I've got a 27, and I could do the 6th root. I'm going to erase some stuff here. I'm going to do something wrong, not wrong, but longer. So I could write 27 to the 5th, c to the 2nd for the top and bottom. But, oops, I made a mistake. 27, not 25. But that's going to be a huge number for the numerator. And I'm not really going to want to take 27 to the 5th times 8 to the 1st for the numerator. So this whole thing that I was going to do, is going to multiply by this form of 1, is really not the most efficient way to do this. So I'm not going to do that, because that's going to be harder. So I'm going to take the 6th root of 8, a to the 5th, b to the 3rd, divided by the 6th root of 27, c to the 4th, and I'm going to change that 27 to 3 to the 3rd. We know that 27 is equal to 3 to the 3rd. And then if I just multiply the top and bottom by the 6th root of 3 to the 3rd, c to the 2nd, I'm really only multiplying by 27 to the 1st instead of 27 to the 5th. So what that yields now is the 6th root, 3 to the 3rd, 27 times 8 is 216. So for the numerator, I get the 6th root of 216, a to the 5th, b to the 3rd, c to the 2nd, divided by the 6th root of 3 to the 3 plus 3, or 3 to the 6th, c to the 4 plus 2, or 6. And remember, these are perfect 6th roots because the exponent will divide the root. So that denominator just turns into 3 to the 1st, c to the 1st, or 3c. So the 6th root of 216, a to the 5th, b to the 3rd, c to the 2nd, over 3c. And I believe that this is also in your homework, so you get to in the 7-3 classwork, so you get to try it again. All right, now let's go to 7-4. 7-4, we're going to talk about exponential functions and their graphs. We're going to do this a couple of days here. You have, come off of already doing this on the calculator. We're going to take a look at it in the, we'll use our calculator, but we're also going to do some graphing so you can practice that. So first thing it says is graph the function y equals 2 to the x. So I'm just going to go grab some points from my calculator, clear some stuff out here. I'm going to go y equals 2 caret x. There we go. And I'm going to go back to Zoom 6, and then I'm going to check out my table. And what you should notice if you go into the negatives, that they just keep getting smaller and smaller and smaller. Now, it might not appear, but if you think about it, go back to the original equation, y equals 2 to the x. There's no way for y to be 0. That you can't plug in anything for x so that y can be 0. So I've got to use, I'm going to use, about probably from -3 to 3 for my table. So I'm going to put that table right here and go with, actually I'm going to go -2, -1, 0, 1, 2, and 3. So from my table I got 0.25, 0.5, 0, 1, 1, 2, 2, 4, and 3, 8. So there's no value that you can enter in for x so that y is going to be 0. So there should be, maybe I should do it in a different color. There should be an asymptote, like a dotted line. Okay, should try to get in. This is an asymptote. Which means that the graph's never going to cross that line. So, at -2, 0.25, it's close to 0, but it's not going to cross that line. -1, 0.5, 0, 1, 1, 2, 2, 4, and 5, 6, 7, and 3, 8. So this is kind of what it looks like. And this arrow implies that it's not going to level off and go horizontal, that it's just going to kind of hug along but get ever so close and close and closer to the x-axis. Label our axes. On y equals 1/2 to the x, I'll go back in. Now a couple of ways to enter that in. If you're going to do 1/2, then make sure you do parentheses. Like that, or you can do 0.5 in there. So when I graph that one, it looks like it just reflected over the y-axis. And you should see that happening in the points as well. So my table of values for this graph are going to be -3, 8, -2, 4, -1, 2, 0, 1. You should notice it's going through 0, 1 in both cases. 1.5, 2.25, and 3.125. So now I still have an asymptote along this x-axis, y equals 0. It's just been reflected over the x-axis, the y-axis. So -3, 1, 2, 3, 4, 5, 6, 7, 8. And so it's going to kind of, again, look like it's hugging that x-axis, but it's never going to cross it. So as x approaches negative infinity, y approaches 0. And as x approaches now to the right here, here would be infinity out here. Here would be negative infinity way out there. So as x approaches infinity on this one, y approaches 0. And that line y equals 0 is called an asymptote. An exponential function is a function of the form y equals b to the x, where b is a positive and b cannot equal 1. Otherwise, it would just be a line. The domain, if we look at our domain on the graphs above, left and right, the domain was all real numbers. But our range, in both instances, was y is greater than 0, unless we perform a transformation, sliding it, left, right, up, or down. If b is greater than 1, then the function is a exponential growth example. If it is between 0 and 1, then the function is an exponential decay example. You should have seen this in the Survivor lab. So now, let's draw the graph of y equals 5/2 to the x. Okay, so I'm going to plug this in to my calculator again. So I can just go over there, change that to 5, and look at my table of values. So I have negative 2.16, negative 1.4. There's that 0, 1 again. 1 is 2.5, 2 is 6.25, and 3 is 15.625. Okay. So, I do not have enough room here. I don't know. Maybe I do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, looks like I do. All right. So, negative 2. Again, remember we've got an asymptote. And then we have negative 2.16, 0.4, 0, 1, 2.5, 6.25, and then 15. Just a little bit above that. So, here we go. Okay, so there is y equals 5/2 x. Now we're going to be graphing more than one graph here, so I'm going to label it. Here's my x and y, labeling of axes. Label axes. And then I'm going to use the graph, estimate the value of y when x is 1.3. So 1.3 is over here. I'm thinking it looks like about 3 point, if I go up here, about 3.2, 3.1. There's my approximately symbol. All right. Then draw the graph of the image of the graph under a reflection in the x-axis and the y-axis. Okay, so I'm going to do the x-axis. So I'm going to do a different color. For the x-axis, I'm going to just flip all of these points over the x-axis. And so I'm obviously not going to be able to get that 3. I would be going over 3 and down negative 15. So I'm just going to kind of go like this. Okay, and that would go like that. So that would be number 1. And then I'm going to do over the y-axis, so it's going through that 0, 1 again, but now there's, and then remember they have to go and be the same distance from the axis and be perpendicular. So 2, little bit, 1, 2, little bit. All right, there we go. Okay, so that was labeling it 2. Then it says write the equations for the graphs drawn in part C. Well, when you reflect over the x-axis, you should negate the y. And when you reflect over the y-axis, you should negate the x. You should notice that. So, you know, if you take the blue graph here and you look, all the x coordinates are the same. It's just you negated the y's. If you look at the red graph, my number 2, I negated all the x's. The y's, the heights are all the same still. So the equation would be y equals negative 5/2 to the x. We've already talked about reflections over the x-axis. You're negating the y, but then you'd have to solve it for y, you'd have to put a negative in front of the 5/2 x. For number 2, it would be negate the x, so it's going to be 5/2 to the negative x, which is equal to, from our exponent rules, 2/5 to the positive x. If you want to plug those in your calculator, you will see they will give you these graphs. Okay? So negative. So if I do second, delete, and I insert a negative here in front of the whole thing, and I hit graph, there's that reflection over the x-axis. And if I then get rid of that and I go up and I negate, let's get up there and do second, insert, put a negative up there, and I negate the x, and there's that reflection over the y-axis. And if I change it around, I go to y2, and I do 2/5 to the positive x, and I graph that, I should get just one graph, because they're the same in y1 and y2. So remember to negate the y. And so on this first one, again, when I negate the y, I really had negative y equals 5/2 x. But then I want to divide both sides by -1, which brings me to y equals negative 5/2 x. All right, next page. Now, we're going to learn more about this thing called the number e. The number e is an irrational number for right now. I'm just going to have you trust me on that. I believe it is second divide on your calculator. So you can look that up, and it will give you this part of this number. It is irrational. We're going to learn more about it in another chapter, but it comes into play here, and it, you know, that means non-repeating. Remember the nit nerds, non-repeating, non-terminating. So, non-repeating, non-terminating decimals. They cannot be written as fractions. Okay, so if we're going to graph y equals e to the x, I'm going to go back, go in here, I'm going to clear these, and then type in, so second divide to the x, and I'm going to hit graph. And it's an exponential. It's exponential growth. So here's a couple of decimals that we'll need for our table. So I have -2.135, -1.367, 0, 1 again, 1, 2.718, 2, 7.38, and 3 is 20. So 0.086, so I think I'll probably just go up to 2. So -2 is real close to 0, -1 kind of same thing, 0, 1, 1, 2.7, 2, 1, 2, 3, 4, 5, 6, 7.3, and then 320, it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It's like way up here. Ooh. So it's real steep, real quick. So x and y axis, we remember we've got these asymptotes on these exponential graphs. This is exponential. This is exponential growth. All right, now here's another application. It's number 11 from page 303. The population of the United States can be modeled by the function p of x equals 80.21 e to the 1.131x. Next, where x is the, e to the 0.131x, where x is the number of decades. Remember, 10-year period since 1900, and p of x is the population in millions. Okay, we'll remember that. So, graph p of x over the interval 0 to 15. So let's take a look. So go back in, y equals, clear this out, 80.21. Now, if you remember from your Survivor Lab, the 80.21 is the initial amount, so that'd be your initial population in millions, so like around 80 million. E would be the growth factor, so second divide is E, and it's already got parentheses, so I'm going to do that to the 0.131, so I'm going to close that parenthesis around that. You could put it inside. You could put the 0.131x inside, but usually it's on the outside. And then if I hit graph, I'm not really seeing too much. So I can see my table. If you look at 0, it's at 80.21. So I'm going to go in and change my window because it talks about graphing it in the interval 0 to 15. So I'm going to make x min 0, x max 15, and I'm going to change my y. So my y min can be -10, that's fine. But I'm going to make that y max, I'm going to try at least, I mean at 0 it was at 80. So I'm going to try like 500 just to see what that looks like. I was just kind of looking at the table. And when I graph it now, I get something. I get a better picture. Okay, great. So now I want to look at this from, so I'm going to take a look here. I don't really care about the negatives. It's a real world problem. So I'm going to look at 0. And it said to go to 15, so I'm going to grab some of these points to write down in my table. And this is what I want to graph to 572. Okay. So I need to think about how I'm going to graph this, set this up. So I noticed at 15 it was at 572. I might have to check back with the rest of that. So I'm going to go and look here at 0 was about 80.21. And I'm going to go maybe by 2's here. 2 is 104.24. 4 was 135.46. 6 is, I have to go back and check that one out. Six is 176.03. And we know 15 was 572. So 8 was 228.75. And then 10 is 297.3. And I just need to get 12 and 14. I didn't write those down. 12 is 386.31. And 14 is 502.02. And then we had 15 is 572. So when we're setting up our axes here, I need to somehow get to 500 on the y-axis because this is the population in millions. And this is the number of decades for that x and y axis. Okay, so this was actually p of x. And this was actually p. No, it was just x. Sorry about that. Okay, so now to set this up, I think maybe I can go by some sort of, let's see. Maybe I could go 4 and make this 100 by 25s maybe. So 1, 2, 3, 4, 1, 2, 3, so make this 200, 300, let's see if this fits, 400, I have to kind of go up there a little bit. And then along the side here, I think I can count by 1, so 2, 4, 6, 8, 10, 12, 14, there's 15 and 16, and then we're ready to plot. So 0 is at 80, 2 is 104, 4 is 135, 125, so about right there, 6 is 176, 8 is 228, 225, so right above that. 10 is about 300 almost, right below it. 12 is 386, so 350, 375, so probably a little bit there. 14 is 502, so now I'm up high. And 15 was 572. So, all right, so there's our graph. And if my points aren't exactly right there at the top because I ran out of space, but they are pretty darn good. So graph P of X, I did that. If the population of the United States continues to grow at this rate, predict the population in the years 2010 and 2020. So 2010, so let's think about this. X represents the population in decades, 10-year periods. So if we take a look at this, 0 represents the year 1900 because it says since 1900, number of decades since. 1 decade would be 1910 because that would be 10 more years on to 1900. 2 decades, so this is what X is and this is the years. So 2 decades would be 1920. So if we jump up to 9 decades, that should be 1990. And 10 decades should be 2000. So 11 decades should be 2010, and 12 should be 2020. So that's what I'm going to use to answer down here. 2010, we had 297.3 million people from the table. And for 2020, we'd have 386.31 million, which we could, write out if we wanted to. 300, we just put a whole bunch of zeros at the end here and change that to a comma. 386 million, and so on and so forth from there. All right, that concludes this lesson. Sorry it was so long.